My name is Ian Sales, and a few years ago I wrote a book about, well, a quartet about the Apollo program, and I wasn't clever enough to reject moderating this panel. So I'm stuck with an astronaut, 2 scientists, and a Hugo Award nominee. So I suppose the obvious thing we ought to talk about is what the Apollo program, begin talking about, is what the Apollo program did when it kicked off. So there is, for example, the argument that it kick-started the semiconductor industry. So would any of the panelists like to take that? And
well, actually, since in my other life I'm an experimental solid-state physicist, I suppose I could address that a little bit. Actually, it's true. When integrated circuits were first invented, the idea that you can put not just one transistor on a chip of silicon, but put dozens, hundreds, maybe someday even thousands of circuits on the same wafer, the world reacted to this invention with a great yawn, because why in the world would you need more than one transistor on a single piece of silicon? It was a completely useless thing. Somebody said, well, you could make perhaps computers that only had a few chips, but what's the point? A computer's as big as a room anyway. Maybe you could make it as big as half of a room. But there were 2 entities that were very, very interested in making computers tiny. And one of these was the United States Air Force, that wanted to make computers that could guide missiles and make them hit precise targets 10,000 miles away. And the other was NASA, who wanted to make tiny computers that could help navigate spaceships to the moon. So the integrated circuits were funded by a joint program of the Air Force and NASA to develop tiny computers, eventually becoming the Apollo guidance computer, a little computer that has about 1/1000th the processing power of my little telephone. So between the 2 of them, the Air Force and NASA, we invented the whole idea of a computer that would be smaller than a room, that you might eventually carry around or even send to the moon, or Moscow, whichever.
May I just put in one little historical fact? Integrated circuits are not a result of solid-state physics. The first integrated circuits were actually inside vacuum tubes, and they developed in the 1920s. Somebody tried to do it, put a whole radio in one vacuum tube by using integrated circuits in a vacuum tube. It didn't go anywhere, but you know, there's nothing new under the sun.
Jeanette, perhaps you want to tell us about how computers are used in NASA today?
Well, the cool thing is that I think just the start with the integrated circuits and then having the Apollo landing kind of made people think that, well, what else can we do? And so right now what we're doing is we're building the SLS. And that's going to be the next Saturn V type rocket, the largest rocket in the world that has ever been built. And so right now, one of the big things that we're trying to do is take everything that was done on the Apollo era, where they had like maybe 1/1000th of the capability of your phone there, and trying to integrate all of that, use precision machining, friction stir welding, and all of these new techniques to build the Orion. And so all of that's going to be highly, it's going to integrate all of the state-of-the-art technology when it comes to computational methods. Even the display panels, it will be similar to, you know, the upgrade in the jets from analog to digital panels in the jets. So there's so much more that we're going to do when it comes to Artemis, which is the Apollo follow-on. So Artemis, we're going back to the moon, 2024, but it's not going to be the same this time. We're going to try to stay on the moon and develop, you know, people want to call it a colony, but really it should be, we're going to investigate the moon, we're going to do all the science, but we really want to develop it as a test bed to go to Mars. So all of the things that we're doing with solid-state circuits, propulsion materials, everything, we're going to try to integrate that. And it sounds like, oh, it should be easier than last time. No, what they did last time was incredibly hard. It was incredibly hard, and they made it look easy. So now what we're going to try to do is we're going to try to repeat it. And I know people are like, well, you've been there, done that. It's still hard. So 2024 is the mark in the sand, but if it takes us a little longer, don't fault us.
one of the things, I think it was Gene Cernan said that Werner von Braun had reached forward and taken part of the 21st century and brought it back to the 1960s. It's really difficult to understand today how radically advanced everything in the Apollo program was. So what's actually happening is that the rest of the technology on the planet is now catching up to that one area of extremely advanced technology. And that's why it feels like, well, shouldn't we be able to do more? It's like, no, they stole part of the 21st century and just had it back then.
Of course, in the early days, computers were human beings, weren't they? So,
yes.
As you have in your book.
Yes. Yes, well, yes, I will talk about that. So the word computer used to just mean someone who computed. And when you were looking at the Gemini and the Mercury programs, what they were doing was women, vast rooms. They used to just do the math by hand, sometimes with a mechanical calculator, but mostly with a slide rule and a pencil. And they would actually say, how many girl hours is this going to take? JPL, Jet Propulsion Laboratory, had a policy that they did not hire men for the computer department. They only hired women because they had a better work ethic. I have no comments on that. But when we were looking at Apollo, because it's an extremely dangerous thing. When you're going to the moon, it's like trying to skip a stone off of a pond on the other side of the planet, but you only have a pencil width of trajectory that you can throw that stone in. If you come in too fast, too steep when you're coming back to the planet, you burn up. And if you come in too shallow, you skip off the atmosphere and just go out into space. And you can't come back. And so the margins are incredibly narrow. So for redundancy, they had a computer on board, and they also had a computer department back on the planet, and they still had the women who were ready to do the math. And there was at least one point when Jim Lovell had to do the math by hand on the spacecraft, because the guidance computers were off.
So there's one unintended consequence then, is the fact that women were ousted from computing, not just in NASA, but also in industry as well, because the early programmers were all women, and then the men came along and thought, I can do that, but I want more money. And there were cases of women who had men putting over them, but the women were doing the job and the man was taking the salary.
This is the story of our lives. You were saying something about the math that is still used.
Oh yeah, we're still using the exact same math that the women did for the Mercury and Apollo program. It's the same math. It doesn't change. And so that's why it's important to say that the work that they did early on by hand, even though now it looks like we're using computers to do it, it's still the same. It hasn't changed much. And in fact, probably, I think, and I haven't verified this, but even the stuff they did for Apollo, we're going back and looking at all of that data. And don't be surprised if we try to repeat it and do the exact same thing and then try something new. Because it was really phenomenal what they accomplished. And I don't think people understand how difficult it was, what they did. Even though their budget was plussed up and they had almost 500,000 people working on it. Now we only have about 52,000 people, and our budget is 1% of 1% of 1% of the budget, 1% of 1%. I got to say it right.
This is Apollo 8, not 11. Sorry, Apollo 13, not 11. But when they were working on the trajectory to get the Apollo 13 astronauts back, they had a room full of people who did math to come up with an answer. And very recently, someone decided to try to run that same situation through a computer, a modern mechanical computer, to see what it would come up with, and it came up with the exact same answer.
When there's an answer, there's an answer.
Yeah.
So one of the things that does, what Jeanette mentioned, was the fact that the Apollo program was massively documented. There's there must be tons and tons of documents and footage. So do either of you two, have you made use of any of that documentation in your day jobs?
Well, mostly the documentation I've been interested in has been what we've learned about the moon. And it's actually just sort of fascinating sometimes to look back on what they were thinking the moon was like before we landed on the moon. When you look at the very early documentation, when they're planning the Apollo, and oh man, they got a lot of things right, but they got a lot of things really very, very, very wrong. They had no idea, for example, how gritty and kind of even pointy the lunar regolith would be. In fact, a lot of the scientists at the time thought it would be very powdery, and that there could even be giant lakes of dust that you could just disappear into. Well, that turned out to be a flaw. I've worked a lot on the question of how can you make things out of lunar materials. And the first thing you want to make is oxygen, in fact. But before the Apollo program, there were people who were looking at that problem and saying, oh, how could we generate oxygen from lunar materials? And they said, well, most Earth rocks actually are hydrated minerals, so we will just bake the lunar rocks and get the water out from the hydrated minerals. As it turns out, none of the Apollo samples were hydrated minerals. They were all, you would call them bone dry, except that actually bones are hydrated minerals, so they're actually far, far drier than bones. And that was something that was unexpected. They didn't realize that the lunar surface would be so completely dehydrated, except that we learned somewhat later, in fact, just in this most recent decade, that we totally misled ourselves by learning about that from the Apollo samples. That the Apollo missions all went pretty close to the lunar equator. And the rocks at the lunar equator are very dry. They've been baked out. They have no hydrated materials. But when you go up to the high latitudes of the moon, when you get up out of the tropic regions, in fact, there's a lot of hydrated minerals on the moon. We learned this from the Chandrayaan orbiter, which was an Indian project, but had a lot of NASA collaboration, and we've now done infrared mapping of the moon saying, well, yeah, all the places that we didn't go to with Apollo have lots of hydrated minerals. And of course, we now know that at the very, very far north of the moon, and south as well, there's actually ice, literally ice in the permanently shadowed crater. Another thing that we didn't learn from Apollo, but have learned since then.
And of course, Buzz Aldrin's boot was very hydrated.
Well, except inside the space.
David?
If you look back, there were lots of different ideas. I mean, you talked about seas of dust. Of course, there's Arthur C. Clarke's famous story of Fall of Moon Dust. Excellent story even today, even though it doesn't fit with what we discovered. And this was one of the points of we were putting forward in our cosmic study, is that you've got to go to the moon. If you want to go to Mars, you've got to go to the moon. It's very difficult, it's dangerous to go to the moon, but at least if something goes wrong, you're 3 days away. If you're going to Mars, once you're going to Mars, you're 2.5 years away. And if something, because you can't get back to Earth, your orbital dynamics haven't changed. The term computer, I know, was used in the 18th century for people who did the sums. That was in the Royal Greenwich Observatory, had computers then. There were guys, mainly men, who did the sums of orbital dynamics and solar eclipses and so on. And the maths hasn't changed. We just have better adding machines to do it.
Moving on from the technology, there's an argument that the Apollo program was the biggest socialist program that the US government has ever undertaken. They built schools, they built infrastructure, they uplifted entire areas of the US simply in order to provide the support and the development for the Apollo program. So, any thoughts on that?
Well, at the time, it was important for the U.S. to beat Russia, and they were willing to invest to do that and to do something unique. And then we also, having a President JFK give that legendary speech in Houston, we had a mandate to go forward, beat the Russians, and show how great the U.S. is. And as part of it, But the end result was phenomenal. It was amazing because, like Houston, you know, under Lyndon B. Johnson, Johnson Space Center was developed under that. We had Kennedy Space Center built up under that. And what we did was create a lot of jobs. And not only that, it kind of inspired a generation of scientists as well. So even though there was this initial reason behind doing that, the end result was remarkable in how we built the U.S. economy. You know, we spent money to build our economy. And when I'm asked about, you know, how can a government justify investing in space exploration when they have other social issues in their country that they need to solve? Well, my answer is always that the investment that you make in your space exploration program will give back in the development of jobs, but also inspiring the next generation of engineers and scientists and mathematicians. And so the investment to me is always worth it. And as you can see after Apollo, how many students, I mean, I wasn't born, I was born a year after Apollo, but even I was inspired by watching Challenger. Even though watching it explode, it still inspired me that I want to be a part of that, even though there's a risk to it, and that these people gave their lives to try to further our knowledge. So the investment that you make, regardless of the reason, the results are there, and you can't mistake it. We really want to do Artemis again and kind of regenerate those ideas to inspire the next generation. You can create jobs. One of the things, I went to NASDAQ recently with the CFO of NASA, and you know, at first I was like, why are we going to NASDAQ? But one of the reasons is a lot of commercial companies are going to get involved. And the NASDAQ CEO, Adina Friedman, mentioned that it could generate about $1 trillion from all of these new companies over the next 10 years. So an investment in space, it actually can help your economy.
Can I just go back to Arthur C. Clarke and Stanley Kubrick? In the film 2001, which came out just before, well, at the height of the Apollo program, there is the famous scene where you have two groups of ape creatures lining up across a water hole, making rude gestures at each other, and the threatening gestures. Well, in 1969, the water hole had become the Atlantic Ocean. Leaders no longer had fur coats, they had business suits. The rude gestures included things like Khrushchev banging his shoe on the desk at the United Nations, insulting the British Prime Minister, and farts and grunts were strategic nuclear bomb tests. But frankly, same old, same old. In one aspect, these Apollo program, and of course there's a famous cut at the end of that scene where the bone is thrown into the air and it becomes an orbital space bomb or space station. And quite frankly, same old, same old. In political terms, the Apollo program was a primitive simian tribal threat display, I'm afraid. And just like such, the threat display, as soon as the losers had been publicly humiliated, everybody lost interest and went back to watching baseball. Now, to me, there is another legacy of the Apollo program which most people don't see. It's not the Apollo program on the moon, it's Apollo Soyuz that followed on, and then Skylab. We have an international space station. It's international. We are cooperating with our former enemies. This is unique in scientific and technical situation on the Earth today. I mean, even though tensions are building up, we're still up there in space working together.
Jeanette?
I just wanted to add that that is one of the most phenomenal, remarkable relationships, is that you can watch the news, and I've had kids ask me, well, aren't the Russians our enemies? I said, well, I've been there, I did all the training with them, I went to Kazakhstan even, and the relationship is remarkable. And so even though the initial reasons that we started out with doing the Apollo program, it all kind of got washed under the, well, politically it didn't, but at the end of the day, going to the moon was really not just the United States. And there was even a discussion on which flag we would plant. But the plaque that was planted was, you know, for all mankind. So the fact that we can work so well together for space exploration, you know, it goes a long way to say, well, you know, diplomacy there is perfect. It's hard to do it in other places.
So one of the things that's interesting about that is that there is a law on the books right now that we cannot allow anyone from China on the ISS. So when you're looking at the effects of diplomacy on Earth and in space, you can spot where those tensions are. And I look forward to that law going away, because I do think that the international aspect is, yeah, Artemis is going to almost certainly.
It's not a done deal yet, but you know, going back to the moon is not, again, it's going to be what we like is you don't go as the United States, you go as the human race.
But one of the things, just to address the jobs thing that we've been talking about, the reason that most of the space centers are in the South in the United States is because that was the area that was most economically disadvantaged. And it was a way of inserting federal funds into those areas. It was a jobs creation program, absolutely. But the other thing that was interesting about the Apollo program was that the science was really an afterthought. I'm not kidding. They're like, we're going to go to the moon, and everyone's like, what are we going to do when we get there? And like, well, maybe we should bring some rocks back? Yeah, so geologists, but we didn't actually send a scientist to the moon until Harrison Schmitt with Apollo 17. And so the thing that's exciting to me about Artemis is that we are thinking about the science, and yes, it's a jumping point to Mars, but we're thinking about the science and sending people who are not just fighter pilots. Nothing wrong with fighter pilots.
It's also worth pointing out that Schmitt was pulled forward from Apollo 18, I believe. So it could have ended without a single scientist on the moon. The thing with the International Space Station, though, is it strikes me it's more of a marriage of convenience than anything else. I'm pretty sure if the US had managed the same political will as it had for Apollo, they would have gone ahead and built one of their own. And it's also slightly worrying that 30 years after the Soviet Union fell, children are still thinking of the Russians as the enemy. So, any points?
Well, I think you do have to think of the International Space Station as an incredible job of international cooperation. There's more than, we say that's the US and the Russians, but actually there's more than 20 nations that are collaborators in the International Space Station. There's European astronauts fly, well, not every mission, but nearly every mission. There's a lot of European astronauts on the International Space Station. It really is international. If there's any of you that are under 19 out in the audience, I can't actually see the audience, you're sort of invisible behind the lights, but if you're under 19, then for your entire lifetime, there have been humans living in space. There has been continuous human presence in space since the year 2000. There's never been a moment that somebody is not alive and working in space. And in terms of going forth and moving out into the universe, that's really a remarkable step. We know how to live in space now. We've done it. We've been doing it. We've been doing it for nearly 20 years now. That's not an absence of progress. Things are moving forward.
Just a couple of things. Plus ça change, le plus c'est le même chose. You talked about when they devised the Apollo mission, science came second. Well, first of all, the International Space Station in the United States was funded as a foreign policy initiative to provide work for Soviet missile engineers, so they wouldn't go and work for North Korea and Iran. That's what got it through Congress. In the same way as the boost the economy in the southern states was strong-armed by Johnson, who was probably the smartest congressional operative. Yeah, precisely. And he made sure that he would get it through Congress, provided a lot of money went down south. Okay, that's internal politics. And the International Space Station, actually, NASA's original plan, or the way it worked out was they were going to build the space station, run it for about 2 years, and then put it in into the Pacific Ocean, and then start building a lunar lander with the cash flow. And this would have been a diplomatic disaster to have spent $100 billion building something and then just, oh, it works, that's fine, drop it in the ocean. And they suddenly realized that they actually had to do something with it. And there was about 3 or 4 years of embarrassment by both ESA and NASA as they rushed around trying to find science projects that were worthy of being carried on the space station, because you can't put anything up there. It's got to be good science. It's too expensive to do anything else.
And just to add
That's
on
a
to that,
bizarre anecdote, and it has no relationship to reality whatsoever. There was never any plan to put the space station up and dump it in the ocean in 2 years. I've been involved in the space station since '88. There was never a plan to put it up and not do anything and dump it in the ocean. It did not happen.
Well, and you know, there is this initial idea that they had to prove that they can do this, and it was initially, like Skylab, it was an experiment. But it was an experiment that kind of grew and grew and grew, because once the entire space station was built, then it's like, oh my gosh, so now we can actually utilize it. So now we're in the phase of utilization, and we're coming up with more experiments that we can do, because our next steps, if we want to go to the moon, we have to do more experiments on the human body. And granted, some of this is, you do the fundamental research and then all these other ideas kind of fall out of it. And I think that's what, you know, it wasn't to put it in the ocean, but it was really to figure out, it was an experiment, if you think about it. So right now, even the ISS itself is an experiment in and of itself. It is the world's largest floating laboratory, but it has to be maintained, it has to be upgraded. Can we try lithium-ion batteries instead of this nickel-based batteries? Solar array wings, how long are those gonna last? Like with Mir, the space station is gonna last a lot longer than we ever expected. And so when you have this longevity, you kind of like, well, we didn't expect that, what else can we do? And I think that's what's going on. And so everything that we learn in low Earth orbit, we now realize that we need to take all of that, transfer it to the moon, prove it out again, further away from the Earth's protection. That's the big thing. We didn't, early on, we didn't realize the effect of taking away gravity, the effect that it would have on the human body, the effect of, like, even when you burn things in space, things change dramatically. So it is kind of interesting that some of the things were an afterthought, but I think it was because we were surprised that it worked. And so, okay, so what else can we do? And hopefully in the future, we'll see. It may be like that for a little while on the moon, because it's going to be incremental, everything that we try to do. And at least this time, we do have a little bit of forethought that, well, if it does work, what are we going to do next?
So one last point for discussion. So I suppose it's a bit of a stretch, but you could say that the continuing missions sent to the moon are a form of legacy, which means that we've now actually gone and colonized the moon, unfortunately with tardigrades, not with human beings. So are they teaching tardigrade in NASA?
I wish I could be a tardigrade. No, they can survive in anything. So the tardigrade experiment, we haven't done anything like that. I think ESA did that experiment. Or was it Israelis? Okay, it was Israelis. And so studying creatures like that, one of the things that I want to learn is, how do they survive? What kind of radiation protection do we need? How can we develop suits that can completely protect us from the radiation? Because as we get away from the Earth's protection, the amount of radiation that you'll experience is going to be a great deal more. I can't give you the exact number than what we're experiencing in low Earth orbit. So studying creatures like that, we're trying to learn more about the human body or develop countermeasures on how we can survive further and further away from Earth.
Jumping off of radiation, one of the things, and the prepping for the moon and the things we've learned from the ISS, one of the things that's interesting is you would expect astronauts to have a higher cancer risk because of the increased radiation. And it's turning out that that's not actually what's happening. We're not seeing a higher incidence of cancer among astronauts. And the Apollo era astronauts, the ones who actually really, left, there's no, and it's a very small sample set, but there's no increase. And the cosmonauts? The cosmonauts also, thank you. The cosmonauts also don't see it. But, and this is an important thing, and one of the accidental legacies of the Apollo program, because it was, there was an initial policy to not accept women into NASA as astronauts, what that means is that our sample size for this is we've got 537 people have been people have been into space. 64 of them have been women, and one of the things that we know from Earth, from some long-term studies, is that women, the incidence, basically radiation affects women at about a 10-fold degree that it affects men. But we don't know what that's going to be like in space because our sample set is so tiny. It looked like you were going to, okay. So basically we need more ladies in space.
Yeah, one other point, just beyond low Earth or in low Earth orbit, like the International Space Station, you're protected by the Earth's magnetic field from high energy cosmic ray bombardment. It's deflected away from the Earth. Once you get beyond low Earth orbit, go to the Moon, you're exposed to this high energy cosmic ray bombardment. Now, the Apollo program missions were relatively short, and we've only got a very, very small sample, so we don't know what that's going to do. But if we go to the Moon and have people up there for quite a long time, studying the effects, or trying to avoid the effects of these high-energy cosmic ray particles is going to be crucial if we're going to go to Mars and not have severe physiological effects afterwards.
It's not just on the humans, it's also on the electronics as well. Jeffrey?
Yeah. Mostly what's unknown right now is what the effects are of the high-energy galactic cosmic rays that are basically iron nuclei and heavier that are moving with, GeV energies and sometimes. And it's completely unknown. We don't really know what the effect is going to be on humans. I know the effect on semiconductors, but whether it's going to be tremendously damaging on humans is something that would be very, very useful to find out. We don't know.
And so when it comes to radiation, it's always the amount of time that you spend in the presence of the radiation. And the good thing for the Apollo astronauts is that they didn't spend a whole lot of time in that. But if you're going to spend 30, 40 days around at a gateway near the moon, you're outside of Earth's protection. And so that amount of time, that's what is unknown. So we're going to start looking at the length of time that the human beings, and that's why you'll see that the ISS expeditions became longer and longer. So at first we weren't sure if 2 months was going to be too long, is that too much radiation? Then it was 3 months, and now it's up to 6 months. And we even had the 1-year study, but the cosmonauts, the reason it's important to note that they haven't seen these high rates of cancer is that they've spent more time in space than most Americans. And each cosmonaut they fly repeatedly, but you don't see these high rates of cancer happening. So what's going to happen when we get outside of that protection is the big unknown.
And I think the thing that Jeff was saying is that basically not all radiation is created equal. Like we say radiation and say, oh, but radiation is, there's a lot of different things. So that's the thing that we don't know. One of the things that is cool is that the astronauts will actually see a streak of light go through their vision, which is, you want to explain that? Because I've forgotten the science of it right now. My brain just went, there's a word, and you're not allowed to have it.
Yeah, there was one of the Apollo astronauts reported it, didn't they, seeing the flashes?
Yeah, all of the ISS guys. Yeah.
And there was this thing sparkling outside the spacecraft, and
That was...
that was your end. So.
It always comes down to that with you, doesn't it?
So they were polluting space. That's one of the legacies of Apollo, polluting space right from the very start.
Yeah. The galactic cosmic rays are intensely difficult to shield against. because they have such high energy. You can shield against some of the lower energy things, such as the Earth's radiation belts, with only a few centimeters of aluminum. But the proposals for long-term habitats on the moon very often have the concept that, well, you put a habitat on the moon, but then you cover it with lunar dirt, what we call regolith. And to shield from the galactic cosmic rays, you need more than a meter of dirt piled on top of the regolith. So if you see the artist conceptions of lunar habitats and say, well, you know, how come they're burying it with dirt? Well, that's why, for protection against the GCRs.
It's time for us to draw this to a close, I think. So if we just, any last thoughts before we finish?
Just to add on to what Jeffrey said, the lava tubes. So they're looking at using lava tubes on the moon for habitats, because you are, and hopefully it's not one that will collapse, but you have that protection on top. And then you have a habitat made of, you know, impregnable with water particles to protect. So.
One of the other more humorous suggestions for protection from cosmic rays on a long space mission is you use water, about 3 meters of water. But the water is perfectly good water, so you use it on the mission and put what remains back into the tank with a suitable separation. What you don't want is a leak, inner hull leak at the end of a mission.
So you're saying you use the water and then you put it back in the habitat, so it all comes back to pee again, I tell you.
So I guess to close out, one of the things that we have left on the moon is 100 bags of poo, which they actually want someone to bring back to Earth to see what the effect of being on the moon for 50 years has been, which I think I'm like, that's the best science experiment you can ask for. But I think for me, one of the things to think about anytime that you're looking at the Apollo legacy, and we touched on it a little bit, are the unintended pieces of the legacy. Some of those are positive, some of those are negative, but I think that when you go in and you look at it and you look for the unintended biases that were there, you know, the cordless grills that are used are sized for a man's hand. The suits, the space suits, and the gloves, all of these are built for men. And if we examine that and think about that and then apply it to the rest of the way we move through our lives on the planet Earth and look for those unconscious biases, I think that is an unexpected legacy of the Apollo program that can benefit us all right here.
So I suspect there won't be any poo left on the moon because the tardigrades will have eaten it all. Appropriately. So, okay, thank you very much for coming. We hope this has been both informative and entertaining, perhaps one more than the other. And I'd like to thank my panelists. And it's really weird, I can't see you, but I can hear you clapping. So thank you very much.